Um, First, I'll introduce myself. My name is Gus Gani. I'm from Odell Associates. I work out of the Toronto office. We also have, so we are the Cambridge rep in Ontario. And today we're here with a group from Cambridge. Brandon and Jacob will be leading the presentation on high temperature heating and ventilation units using 100% outside air. If you have any questions throughout the presentation, please just drop them in the chat and we'll go over them at the end of the presentation. And any questions following the presentations, you're welcome to reach out to any of your local Odell reps, and we'll be happy to address them. So I'll pass it on to Brandon first, and as we go through the presentation, each rep will anyone from Cambridge will introduce themselves as we go.
Thanks for the intro, Gus, and good morning, everybody. Yeah, I'm accompanied here by Justin Screeman and Patrick Stevens, two of our co-workers, regional managers here for Cambridge, and then one of the other applications, Jacob Wyckoff. I lead our applications engineering team. Justin, you want to share a few words before we kick it off?
Yeah, I just wanted to thank everybody for being here. My name's Justin Screeman. I'm down in Idaho. My family's originally from Canada, and I work for a company in St. Louis, so kind of a trifecta. I support Odell along with the rest of Canada and then a chunk of our United States, mechanical engineer. And I really appreciate everybody jumping on the call. You're in good hands with Brandon and Jacob. I'll hand it back off to Brandon.
Thanks, Justin. We'll pull up the slides here and we'll get going. Well, again, it's a pleasure to get to spend some time with you all this morning. We're going to today unpack what high temperature heating and ventilating units are with 100% outside air, and really just understand these in greater detail. But just for way of context, we here at Cambridge Air Solutions help leaders in manufacturing and warehousing create healthy working environments for hardworking people. And we feel strongly that one of the ways that you can do that is with this equipment. So we're going to spend some time getting down into the weeds and understanding this equipment a little bit more. But we've got three primary objectives for you all today. One, we want you guys to understand the simplicity of design, just how the unit works, what's in it, and just taking a deep dive into what it looks like. We want you to understand how it is inherently safe equipment, and we're going to unpack that more. And then we're also going to go into a lot of detail on the energy efficiency side. We'll get into some of the thermodynamics a little bit about how we look at the capacity of these units. But first, just taking a step back and placing this in the context of some of the trends that we're seeing. Ventilation is really important, especially these days, having gone through COVID. People have a keen eye on what does indoor air quality look like and what role does ventilation play in that. Going back a couple of decades, sick building syndrome and really, really tight buildings, the industry has kind of ebbs and flowed in that. But ventilation is an important topic, and people want to know how does the equipment that they're choosing affect the indoor air quality. The other side of this is energy efficiency. Cost is certainly a result of energy efficiency, but so is the environmental impact, decarbonization. And this is an increasingly important topic in the HVAC industry, especially given the footprint that buildings have in general. But there's a tension between these two, and we need to find interesting ways to balance that. As you increase ventilation, perhaps increase the indoor air quality, the energy usage goes up. And so what's the right balance there, and how can we understand how these two factors work together? HTHV units provide a unique way to really address both of these and to tackle this with a good balance. What is HTHV? If anybody is familiar with this, would you please hit the hand raise button just so I can kind of get a sense of who's familiar with this type of equipment? Have you seen it before? Let me get a sense. So a couple of you. From a basic definition standpoint, HTHV stands for high temperature heating and ventilating. And there's a couple of criteria that you have to meet in order to be classified by this. It's actually a definition that the Department of Energy has created. It requires 100% outside air. It's a direct fired unit. You must have greater than a 140-degree temp rise, and you must be able to discharge air at greater than 150 degrees. You also must be able to meet ventilation and heating requirements simultaneously with some sort of modulating control system. A little bit on the history of HTHV. Back in the 1990s, we introduced a product line under the S-Series nomenclature, and we achieved some really cool results in that we were able to hit 160-degree discharge temperature with a proprietary burner system. And this product line was transformational to the heat-driven, non-ducted market, particularly in warehouses and distribution and manufacturing. It's of course expanded since then, but it was a really unique value proposition then, and it still is now. And it's for three primary reasons. Number one is the lower total install cost when you look at the whole building. Historically, you throw up a bunch of unit heaters, or you'd have infrared heat, and you'd have a number of different systems in order to meet the building's heat load. But with this equipment and the high heat capacity of it, you could use fewer pieces of total equipment. And fewer pieces of equipment means fewer roof penetrations, fewer gas connections, fewer electrical hookups. And so it simplifies the overall installation of the facility and really brought that install cost down. The second is, of course, energy efficiency. The high temperature discharge, and we're going to go into why that is really important, and the direct fired nature of the equipment leads it to being a very efficient usage of natural gas. Being 100% combustion efficient, 92% thermally efficient, basically getting all the heat possible out of the natural gas that's coming into the unit. And so people saw their utility bills decrease as they switched over to this equipment. And then the last part is the ventilation aspect. It's a 100% outside air unit, and so now we have consistent outside air ventilation that was improving the indoor air quality of facilities that has historically relied on natural infiltration. And there's some pros and cons to natural infiltration that we'll get into a little bit later. So I want to make clear a distinction between a traditional makeup air unit and an HTHV unit. And it really has to do with the orientation of the blower and the burner. Perhaps you are more familiar with a traditional makeup air unit in which the blower is in the warm or the hot air stream, pulling air or drawing air across the burner. And that's what you see in the top image there. The discharge temperature of these units is limited just by the practical thermal limitations of the equipment in the hot air stream. And this is opposed to a blow-through unit or an HTHV unit in which the blower and the motor and those critical components are in the cold air stream, blowing air over the burner. And so you can see that distinction. It's an important one, and it's what allows the discharge temperature of a HTHV unit to get as high as practically possible. And that's that in conjunction with the proprietary nature of the burner allows you to hit 160 degrees on the discharge temperature. So again, both of these, there's no heat exchanger losses, there's no flue losses, but that orientation difference does have a big role in these units in general. So some of you guys, jet engines, I like aerospace stuff. This is pretty much a jet engine. You've got intake, you've got compression, and you've got combustion, and you've got exhaust. Of course, we're making heat and not thrust, but the overall configuration of these units is frankly quite simple. Typically, it's a forward curve fan, belt driven. And you can see here the burner is situated just after the blower. You can add filtration, but really all the accessories and whatever you need to install this is in one kind of nice little complete package with a discharge. It's really frankly a simple piece of equipment. You may be asking yourself, are these safe? How can these be safe? We don't have a flue. And so we are discharging the combustion right into the space. So we want to spend some time on this because it is a question we get. Frankly, it's a question that I had when I stepped into this and learned more about it. And I wanted to understand that for myself, and want to be able to share that with you today. An important part of the safety of this design is the safety certification that HTHV units must comply with, and that's this ANSI Z 83.4 CSA 3.7 certification, which really governs the 100% outside air direct gas-fired heaters. There's many things that the units must comply with to be classified under the certification, but two of the most important ones that I'll call out are the combustion byproducts and the maximum limitations there, and also the non-recirculating nature of them. There's a number of combustion byproducts that the units must fall within. Perhaps the most important is carbon monoxide. And the certification requires that these direct-fired units discharge no more than 5 parts per million carbon monoxide. There's some other limitations on carbon dioxide and nitrogen dioxide, but carbon monoxide, given the safety implications, is a really important one. The second one is the non-recirculating nature of these units. Being that we're not recirculating indoor air, you cannot build up carbon monoxide into space. You always must be bringing in outside air. Actually, the outside air is what allows this unit to bring in air and support an ASHRAE 62.1 minimum ventilation. And so we know intrinsically that the outside air is helpful, but it's particularly important in the context of a direct fired unit that the outside air is always coming in when there's combustion, because we don't want to build up any unharmful combustion byproducts. From a practical installation perspective, the units are certified to zero clearance to combustibles, and that's helpful in a number of different cases. I know OSHA is what we use in the US, limits an 8-hour time-weighted average for carbon monoxide exposure to 50. Perhaps you all know more about this than me, but it looks like Ontario Regulation 833 in the IHSA, so to OSHA, your limitations are a little bit lower. You've got a 25 part per million time-weighted average carbon monoxide exposure. But again, you can see, even from a certification perspective, we're considerably lower than the exposure limits for carbon monoxide. So how do we make sure that we've got consistent and adequate ventilation, that we're not building up unharmful combustion byproducts in the space? There's a number of electrical controls designed into the unit that prevent this. The first is an airflow pressure switch. And really, all the switch does is make sure that there is at least the minimum required ventilation across the burner, or airflow across the burner, to ensure proper combustion. If the airflow falls too low, the unit will shut down. There's also a high temperature limit switch on the discharge temperature, preventing excess temperatures from discharging into the space. So if the discharge temperature gets above the limit, again, the unit will shut down in case there's an unsafe condition. And then the third is the temperature control system, which modulates the gas input into the burner to again ensure that the discharge temperature is within an allowable range. So then the question is, what happens if one of these safety controls fails? So we did a failure mode effects analysis where we removed all 3 of the safety controls. We took away the airflow switch, the high limit, and the control system, and we blocked the airflow through the unit. And we said, well, what would happen in the absolute worst case that all 3 of your redundant controls fail? And in fact, we found that the highest carbon monoxide level discharged was 10 parts per million. Again, that's quite a bit lower than the permissible exposure limits for carbon monoxide. So there's a number of things at play here, not the least of which is the safety certification, but really just from a design standpoint, that ensures that these units are safe. But a key point is that the ventilation air and combustion air, they are one and the same. You cannot separate them. So if you don't have proper ventilation, if you don't have outside air, you don't have combustion. And that's really a key point to the safety. So we're going to switch gears a little bit. The next question that people have is, well, you're bringing in outside air. That seems counterintuitive. Isn't that wasteful? I don't know about you all. I'm always telling my kids, close the door, keep the cold air out. They go out and the door stays open. It's ingrained in us. I feel it too. We want to minimize that as much as possible. And while that might be good in sentiment, and to some level that is good, it's also important. So we know a couple things about outside air. One is that every building requires it for human occupancy. ASHRAE 62.1 is perhaps the kind of the best approach that we have to say what is an acceptable level for safe indoor air and how much outside air do we need. Let's do another raise of hands. How many of you all have done an ASHRAE 62.1 ventilation calculation in any of your projects? All right, I got at least 7 of you. Yeah, and we see this a lot too in a number of the specs that we see. Um, it's really an interesting spec, and if you go through it in detail, especially the way that it details the different type of spaces and how much air is required based on the number of people and the type of activity inside the space, but it's very clear that we want outside air, and actually in some cases it's code required. The next thing that we know is that outside air can either come from mechanical ventilation or natural infiltration. And natural infiltration is, frankly, suffers from a number of problems, inconsistency being a key one. Depending on the outside air conditions, the environmental, whatever's going on, whether doors are open or closed, and some miscellaneous fans are on and off. We know that natural infiltration is inconsistent. It comes in where we don't want it, and we just can't really get a good handle on it. And we can't ensure that it's always going to meet the minimums that we desire. Mechanical ventilation, on the other hand, allows for consistently ventilated buildings. You can bring it in prescribed locations, and you can really control the building environment much better. But the reality is that this puts an air load on the building, air that must be heated, especially when it gets cold outside. So if it's 0 degrees outside and that air's got to be heated up somehow. And in many cases, it can be a significant portion of the overall building's heat load, with the remaining part being conduction losses. And so we're going to look at how do you heat the air load and how do you heat the conduction load and what's HTHV's role in that. There's 2 main systems that you can use to heat the air load of a building. One is a traditional indirect fired system. Could be unit heaters, could be others, and then direct fired or HTHV. And so let's look at a little bit more what this looks like. What's the more efficient way to heat the air load in the building? Direct fired is considerably more efficient, consuming about 15% less fuel than an 80-20 indirect gas-fired system, really because of the flue losses that an indirect fired system suffers from. So practically, if we're just looking at the ventilation load right now, just the air load, take a theoretical 10,000 CFM direct fired unit. You bring it in 0 degree air, you heat it up to 70 degrees. This is roughly an 870 MVH output unit. But again, no flue losses, no heat exchanger losses. It's going to be 92% thermally efficient. This is the most energy efficient way and competitive first cost way to heat the air load of a building. But then you say, well, what about the conduction load? What about the skin losses? Because again, as we mentioned, it's a big part of the heat load. So one, you could add more indirect fired systems. You could add infrared heaters. You could add a number of different things to cover the balance of the heat load. Or you could take that same direct fired unit and increase the discharge temperature. Every degree that the discharge temperature is increased above the space temperature is usable to meet the conduction load of the building. So let's do a comparison here. We got the same 10,000 CFF unit in each case, bringing in 0-degree air. The first case we just saw discharged at 70 degrees, and you've got an 869 MBH output. Take that same unit and change nothing but increase the discharge temperature by 90 degrees to a total discharge temperature of 160 degrees. And now you've got a total MBH output of just under 2,000. So the important part of this is the difference between those two numbers. We call that usable or net BTUs. And that number in this case it's a little over 1,000 MBH. All that heat is available to meet the conduction load of the building. Some folks will say, well, a BTU is a BTU. I'm comparing a draw-through unit to a blow-through unit. And I'm meeting this BTU to BTU. But the reality is, if you go one step down and look at the usable BTUs, that number will change between the two. And a blow-through HTHV unit is going to have more usable BTUs to meet the conduction load of the space. If you don't have enough usable BTUs and they don't exceed your conduction load, that's when you can get into conditions in which you're not able to maintain the target internal space temperature. So just kind of looking at that comparison a little bit more, we'll take a theoretical building that has an 1100 MBH conduction load. If we were to use a 160-degree discharge temp unit on a internal design temp of 70, that unit needs to move 10,000 CFM of air. If you lower the discharge temperature, you're lowering the usable BTUs. And the only way to get that back up to meet the conduction load is to increase the CFM or the airflow of the unit. And so you can see that in order to hit the same usable BTUs, that unit would have to move 24,000 CFM of air because of that lower discharge temperature. And of course, if you take this to its logical end, if you don't have any temp rise at all above the internal temperature, you simply can't meet the conduction load. You've only heated the air load. And frankly, you've increased the air load. You end up increasing the air load considerably and just waste energy because you're just doing it in excess. So practically, whenever you increase the airflow of the unit, it's a bigger unit, bigger motors, more difficult install. And so you end up wasting energy and wasting money on units that don't need to be that large. This is Forest Park in St. Louis. It's the Great Balloon Glow Race. I don't know if any of you have ever spent much time in St. Louis. Actually, I think I'm the only one from Cambridge on the call who lives here in St. Louis. This is a really cool event. If you're ever in town, I think it happens in the fall time frame. Go check it out. But the reality is that hot air rises, and this is nice for hot air balloons, but not so nice in warehouses. Stratification can cause problems, uneven temperatures inside of a facility, and people sometimes use HPLS fans or other kind of low-cost equipment to overcome that phenomenon. But with the HTHV unit, discharge temperatures are actually relatively high, usually in the neighborhood of 1,500 to 2,000 feet per minute. So this has a key benefit as it relates to even temperatures and destratification inside of a facility. There's an induction effect that occurs when you're moving air at a high velocity. And in the case of an HTHV unit, for every 1 CFM of discharge air, you end up moving about 10 CFM of building air. And so you can get a lot of movement in a high base space and destratify it really well without adding any additional equipment to do that. So again, not only are you heating the space really efficiently, but now you have a really great system effect that allows you to destratify it and keep temperatures even, not only horizontally, but also vertically without having to add other equipment and integrate them and install them. From a design standpoint, an application standpoint, The equipment is really simple, but also is the application. You don't have to overthink it. Typically what we do is we say, where is the greatest air load? In warehouses, in other distribution facilities, it tends to be near the dock doors, which are opening and closing. And so we usually look and say, where is that? That's where we want to place our equipment. And we kind of take a zoned approach. We look for things like open aisleways because you want movement of air throughout the facility. And if there's some sort of exhaust air or exhaust fans, you tend to want to draw it across the facility. It doesn't need to be overthought. And so in the same way that the equipment's simple, so is and can be the installation in the facility, because you don't need deck work in large facilities to be able to heat it and keep temperatures nice and even. HTHV units can take a number of different configurations, but and perhaps the most common is just a basic rooftop unit or through-wall unit. But again, just want to highlight that these are generally standalone pieces of equipment. There's not a lot of integration with external ductwork and complicated things inside of a facility. There's a gas connection, an electrical connection, and just some way to support the unit. But the small discharge nozzles and kind of just placed appropriately at the recommended height discharge air and keeps air moving throughout the facility quite nicely. So I'm going to turn it over to Jacob, and he's going to spend some time doing a deep dive into the energy efficiency, the thermodynamic side. And I'll turn it over to you, Jacob.
Yeah, thanks, Brandon. See my screen okay?
We got it.
Awesome. Yeah, so Brandon touched on this a little bit earlier, but I'm going to speak a little bit in a little bit more detail on how the design of the unit impacts the overall efficiency. So as he mentioned earlier, with your typical draw-through unit, that burner is going to be upstream of the blower, which is going to restrict your discharge temperature to typically around 120 or less. That's really great if your primary goal is to provide large amounts of CFM as makeup air, things like kitchen makeup air units, paint booth makeup air units, applications where you have a lot of process exhaust and you're trying to make up that pressure differential. Where HTHV becomes very efficient and a great application is whenever you're using it primarily for space heating. So with that burner moved downstream of the blower, you're able to increase that discharge temperature to 160 degrees, like Brandon said, which is going to allow you to provide more BTUs and less CFMs. So our goal in that is to provide minimum amounts of ventilation while being able to provide large amounts of high efficiency direct fire heat into the space. So what's the difference between the two? We've already spoken about how the discharge temperature has a great effect on the amount of net BTUs or usable BTUs that you're providing to the space. But something we haven't talked about yet is that both of these units have constant volume fans. We're selecting our fans. We're talking about our fans in relation to volume. But where we place that blower in relation to the burner has a huge effect on the density of the air that the fan is seeing. And why does that matter? So because the draw-through unit is seeing a much lower mass flow rate and the HTHV unit is seeing a much higher mass flow rate, it allows us to provide much more heat into the space per CFM, per volume of air that we're providing to the space. And how is that? So raise your hand in the chat if you've used this in the past month or so, the convective heat transfer formula that governs our industry. Total heat transferred equals mass flow of air times specific heat of air times your delta T. So we actually have a few people that have used this in the past month or two. So that's actually a little bit surprising because in our day-to-day, we typically see people using the formula down below. Our total heat transferred equals volumetric CFM times your 1.08 times your delta T. And why can't we simply use this? Why isn't this correct 100% of the time? So that 1.08 is a standard correction factor that's only going to be valid at standard conditions, which is 70 degrees and sea level, What that 1.08 is trying to do is it's trying to relate volumetric CFM into mass flow of air times the specific heat of air. And that's typically okay for most of our applications, especially comfort cooling, where you're typically between 55 and 90 degrees or so. But whenever we're comparing draw-through and blow-through units, the temperature difference that we're seeing at the fan makes a huge difference on the amount of BTUs that we're able to provide into the space. And we'll deep dive into this formula into the next slide. The final takeaway that I'm going to try to prove to you guys is that an HTHV unit is able to provide 127% more net or usable BTUs per CFM through that constant volume fan compared to a draw-through unit at 120 degree discharge temperature. So our mass flow rate formula we see up there still at the top right. We know that our mass flow is directly proportional to the amount of BTUs we're providing per CFM. Our draw-through unit is processing 120 degree air at the fan, while our blow-through unit is processing that 0 degree air. That 0 degree air is going to be much more dense. 26% more density, 26% more mass per fan CFM, which directly correlates to 26% more BTUs transferred for every CFM processed by that constant volume fan, just simply due to the density that we're seeing at that fan. Now, what about discharge temperature? We've already spoken about this. The difference in discharge temperature between 120 and 160 degrees leads to 33% more BTUs per hour transferred for every CFM processed by that constant volume fan, just simply due to turning up that discharge temperature from 120 to 160 degrees. When we combine these two effects, it adds up to an even greater difference. So we have the 26% more energy due to the higher mass flow, due to the higher density, the 33% more BTUs due to the higher discharge temperature. Combining both of those effects, we get 68% more BTUs per hour transferred for every CFM processed by that constant volume fan. Now, remember how Brandon talked earlier about separating the conduction load and the air load, and about how every degree we turn the discharge of our 100% outside air direct fire system above the space temperature, we get BTUs that are usable to cover those conduction losses, which is our heat losses through the walls and the roof, through the skin of the building. And for a lot of these applications, that's primarily what we're concerned about. We're not concerned with providing, with over-ventilating space, especially for spaces and buildings without a lot of process exhaust, without a lot of occupants in there. We really just want to be able to heat the space. And the difference is even more notable whenever we're talking about usable BTUs in regards to the discharge temperature difference. So using that same example, but comparing that delta T to our delta T above our space temperature, which was 70 degrees, that leads to 80% more usable or net BTUs transferred for every CFM by that constant volume fan, just simply by turning the discharge temperature up 40 degrees. Having our same, combining those two effects, our same mass flow difference and our higher discharge temperature, that leads to 127% more net or usable BTUs transferred for every CFM processed by that constant volume fan. So what I said earlier, it proves out here in the science and the math, but how does that play out in the field or from the examples that we have? So luckily, HTHV, it's not a new piece of equipment. It's been around for a long time. Cambridge specifically has done over 400 plus energy building studies with utility bills to back up our claims. So we're going to go through one example here, but reach out to your rep if you're wanting to compare it to an alternate technology or see some more examples or see an energy analysis specific to your building. We have decades of experience comparing these to boilers, unit heaters, infrared radiant heaters, makeup air units, things like that. So here's an example of a building in Cleveland, Ohio, roughly 540,000 square feet with 61 dock doors. Before they had a unit heater design, and they were having a lot of issues with uneven temperatures, with cold dock areas, and they thought their gas bills were a little bit high. They came in and they replaced those unit heaters with HTHV space heaters. They were able to achieve more even temperatures and they were able to save energy. So along with being able to get more even temperatures, more comfort for their occupants near the dock doors and having less cold and hot spots, they were able to save 31% in gas, which comes out to $60,000 a year, which can make a huge difference in the profitability of a food distribution warehouse. And ultimately, due to the direct fired efficiency, due to the destratification, they were able to save a large amount of gas while providing better indoor comfort for their occupants. So we touched on adherent safety. We touched on energy efficiency in great detail. Now we're going to briefly touch on simplicity of design of these HTHV units. So the main takeaway we want you to get from this section is that HTHV is going to be a massive value for your money. So you get the very efficient units that's going to last for a long time, that's going to be very simple and require very little maintenance. But you're also eliminating many pieces of equipment to get the same effect. So with one 1600 MVH HTHV unit heater, you're able to eliminate 6 high efficiency 300 MVH unit heaters. You're no longer going to require some kind of auxiliary destratification technology like HVLS fans. And you're no longer going to require some kind of heated DOAS system to be able to provide that fresh outside air. So we often get people trying to compare the equipment cost of HTHV versus other equipment like unit heaters. But really the more apt comparison is to compare the total installed cost of an HTHV unit to a similar performing system that would require all of these that you see on the right. Whenever we're talking total installed cost at HTHV unit, it's going to have less gas piping, less electrical connections, less total equipment to install. Be much more simpler, have much more simple controls, and it's going to last for a very long time with very minimal maintenance. Overall, leading to a massive value for the money for the end user over the 20 to 25 year lifespan of the HTHV unit. So some of the key takeaways we want you guys to come away from this presentation with is 100% outside air direct fired makeup air units. They're not niche in the industry. They're very widespread, used in many different applications, both HTHV and LTLV. The inherently safe design that Brandon talked about. So ventilation is going to be the key for this. And with 100% outside air, where you can't separate the two, ventilation air and combustion air cannot be separated. You're not going to be able to get combustion without also ventilating the space. And safety certifications that require certain limits on products of combustion, certain control safety features. Overall, you're not compromising safety by going with this. You're providing an inherently safe design that poses no danger to any occupant. We talked in depth about energy efficiency and how the density that the fan sees and the temperature rise can affect the energy efficiency of these units. And we went through a building study that shows 40 to 70% energy savings depending on the technology that you're using at the site. And then finally, we talked about how HTHV can provide the lowest total installed cost due to the simplicity design, due to the reduced number of units, the reduced number of systems that you're installing, the less time and materials needed to install the equipment. As Brandon said, these come almost completely ready to go with all the parts and pieces that you're needing. And that's the readiness of install. So Sarah has your contact info, and she's going to send that out to us after this presentation so we can get you your PDH credits. And does anyone have any questions? I think you can throw it in the Q&A or the chat if anyone has any questions. I see a hand raised. If you can unmute yourself and talk, go ahead.
Okay, well, if there's no questions, first I'd like to thank Brandon and Jacob and Justin for your help today. It was a great presentation. If you do have any questions, please reach out to us, your Odell rep, and we'll be happy to address it. But for now, thanks everyone for attending today and hope to be in touch.
Yeah, thank you, everybody. We really appreciate your time. Thanks, Brandon. Thanks, Jacob.
Thanks, Gus. Thanks, Jacob. Thanks, Justin.
Yeah, thanks, guys.
Thank you.